So let's just get started. So this time we just learn about the gradient. So I just want to spend some minutes to review the concept to you. That in the beginning we just want to know the directional derivative, right? So just to remember, if you want to get the directional derivative, three factors you need to know ahead. That the first one is you need to have the service. So that means the question will give you the z is equal to f of xy. Okay, this is the first one. Then the second one is the start point in the xy plane. So that will be x0, y0. And then the final one is the direction u. And u here must be the unit vector. So that means the length for the vector should be 1. Okay? So if you have these three elements, then you can try to get is the directional derivative. That will be gradient vector at p0 dot product this u. So you can see gradient vector just use f functions here, f, right? And you also need to have p0. So based on this, you can get the gradient vector. So gradient vector defined here is partial f partial x at p0 and partial f partial y at p0. Then p0, using this p0 and f, you can get the gradient vector. The inner product or dot product with u, this unit vector. Okay, so then we know how to get the directional derivative by this formula. Then I just give you an example. So I just give this part. Then for this part, we try to think about it. If I give you the function, I give you the surface, z is equal to f of xy. Then I also give you the start point, some start point, which direction can make you to let the function increase most rapidly, right? And which direction can make your function to can just decrease most rapidly. Then the last one is follow which direction your function value will just keep the same, zero change. So based on these three discussions, we can know that if the direction just follow the gradient vector, then the function can increase most rapidly. If the direction u just follow the opposite direction of gradient vector, then that can cause the function decrease most rapidly. Then if the direction just follow some direction which is orthogonal to the gradient vector, then follow this direction, the function value will just keep the same. That means the function value just with zero change. Okay, so then I just also give you an example. Okay, then we just, this is about the application, first application for the gradient vector. Then we just move to the next topic, that we just want to use gradient to get the tangent to the level curve. So that's Thursday. Maybe I just went through this part a little bit fast. So maybe I just spend some minutes to explain this idea to you again. That okay, if f of y has a constant value, that means the return value is always c, following some path. The path here can be represented as r of t is equal to g of t I plus h of t j. So even though maybe we didn't study this part too much, but I just ask you to know that this is just a position vector. Position vector means through this vector we can know the path for this this path just was described as a vector function. Then you can just simply regard gt here as x, then ht here is j. So that you can just treat them as a parametric equations, right? S is equal to g of t, then y is equal to h of t. Then since you just say that following this path, f function always return a common c. So that means if we just use gt, ht as the input for this function, the function value is always c. Okay? So if we just differentiate this equation at both sides with respect to t, so you can see for the right hand side, because this is constant, so when we differentiate it, we can get 0 here. Okay? Then if we just differentiate the left hand side, then we just follow the concept we just learned in section 4 about chain rule. So you can just use the tree diagram, you can get the actual result is just like this one. So we also can rephrase it to become this one. Gradient vector f inner product this one. But this one, because you can see the original one is gt and ht. This is about the position vector. So if we just differentiate respectively, we can get g prime t and h of t prime t. So let's just talk about the velocity vector. So gradient vector interproduct velocity vector is 0. Is 0. That means these two vectors just are orthogonal to each other, right? 两个内积，两个相内积为0的话，这两个向量一定是什么？正交垂直，对不对 ？Okay, so going back to the curve here, so we assume g of t, h of t is are just these points are just describing a curve like this one, green one. So based on this fact, at each point, you always can get its gradient vector. And you also can get its velocity vector because this is a position vector. So its velocity vector, it should follow the direction of the tangent, right? So if the movement is just follow this way, this is the position, then following the tangent, the direction of the tangent, it will be its velocity. 如果绿色这个我们描述它是一个什么位置向量，就是描述它的曲线的位置，每一个点在这曲线上的每个点的位置的话，它的点从这里到这里，因为它是参数是写法嘛，对不对？所以你知道不同的 t 它描述不同的位置。那当你去做想要算它的速度向量的时候，事实上它就是切线的方向，因为就是这边一点点的变化呢，去除以时间的一点点的变化，所以就是它的切线方向。那根据这个推导，我们知道切线方向，也就是速度向量的方向呢，会跟你的 gradient vector 正交，这是一个很重要的性质。因为等一下呢，我会把这个想法延伸到 3D， 也就是它不是只有 g of t、h of t， 它还多了 k of t，k 第三维。所以二维这部分为什么我们要花时间再讲一次？是你务必要搞懂这个想法。velocity 一定原本它本来的它位置如果是这样描述的话 ，velocity 一定是跟它是它切线的方向。那 velocity 经过这个证明，又可以知道说它跟它这个点的 gradient vector 正交，所以我们就得到一个结论：如果你要得到这个 velocity 的话呢，你只要把 gradient vector 算出来，你就可以知道它这个它的垂直方向是哪一个哈。Okay, so I also depict one example to you last week that can you just find an equation for the tangent to this curve at the point -2, 1. So actually this is an ellipse, just like this one, right? Then I just ask you to try to get the tangent line which pass through -2, 1. So for you, actually this is a total new problem for you because we also can use the skill we learned in last semester, which is implicit differentiation, right? Because we can know, we can have this equation, then we just regard this is a hidden relationship between x and y, so that you can use different hidden you can use implicit differentiation to get dy over dx. Then use this one, then you can get its slope for this line, right? And you can furthermore you can just get its equation because you know the slope and you also know this point, so you can use point slope equation to construct this tangent line, right? 上学期其实这个题目对你们讲不新啊，因为上学期我们学过隐函数微分，我们就学过这种问题了，对不对？那这个就是在讲两个变数之间的隐性的关系，所以你可以去算出 dy over dx 的，也就是斜率，那得到这个斜率要经过2跟1这个点，所以你就知道这个斜率有一个点有一个斜率，你就知道可以透过点斜式去取得这黄色线的直线方程式。但这学期我们学的是另外一个看法是什么 ？gradient vector。所以这个题目呢 ，we can just retreat this problem as by using the solution based on gradient vector. So you can treat this ellipse. This ellipse is a curve in the xy plane, right? But you just image that I construct a surface that is z is equal to f of xy is equal to s squared over 4 plus y squared. So when you just face this equation, you need to know actually this is just describing a surface, a 3D surface, right? Because this is z, this is x, this is y, right? So the surface will be constructed in the air here. But what's the relationship between this ellipse and this surface? So we can know this is an ellipse and the value is 2. So we can just regard this curve as a level curve for f of xy is equal to s squared over 4 plus y squared with c is equal to 2. 我们可以把它视同为什么？它是一个 level curve for 这个曲面，但是它的 level curve return 的值呢都是2，对不对？因为这个 ellipse 就是它的最终值是2嘛，所以把它带进去一定都是2，对不对？所以这时候呢，这个观点就不一样了。这个观点是把这件事情当作是 level curve for 这个 surface。Okay, so based on this, we also know that if we want to know its velocity vector, that means this is a tangent line passing through this point. So it must be orthogonal to its gradient vector. Okay, so the first thing for us is try to get the gradient vector first. So based on some calculation, you can know the gradient vector here is -1, 2, this direction. So with this, we know this direction must be orthogonal to is the direction of gradient vector. So then we can just think about that. If any point in this line, xy, any point xy here, then when we calculate the direction from xy to from -2 to 1 to xy, any point, we form a vector here, then this vector should be orthogonal to gradient vector. So that means when we just inner product these two vectors, then we can get 0. So that we can get, actually the line is this one. I just give some computation, but I think you can do it by yourself. But the concept here is very important. OK， 所以我们要建构这个切线的时候怎么做呢？假若这上面的点都是 xy 所组成 ，xy 它是变动的，但是我们要把它规律性找出来。这个上面的任何一个 xy 哦，它跟这个2跟负1这个点呢形成了一个向量，势必跟你的 gradient vector 呢会正交。所以我们利用这样的一个关系呢，可以算出这个直线方程式。OK， so we just spend almost more than 10 minutes to review the concept with about what we just learned last week. So today, I'd like to extend the idea to a 3-dimensional space. So then today we will talk about section 6. Then we will talk about the tangent plane and differentials. So let's just go for tangent plane first. If f of xy, then here we add an extra variable in. So in the past, maybe we just face z is equal to f of y, but right now the function is a 3-variable function. Okay, is equal to c along a smooth curve r of t is equal to g of t I plus h of t j plus k of t k. So you can just make a comparison. You can make a comparison here. This is 2-dimension, 2-variable function, right? And the return value also c. But here, this is the three variables, and the return value is also c. Along a smooth curve, this is for 3-dimensional path. But for 2-dimensional path, you can see here we just have 2 elements, x and y. So almost the same, except that we have an additional variable z here. Okay. So then, if so, then we can just regard this is x, y, and z, right? So we use g of t, h of t, and k of t. It will be c. So we also differentiate both sides. G of t, h of t, k of t is equal to differentiating c. So the result is to be 0, right? Because it is constant. So by the tree diagram, we can know f is determined by x, y, and z. Then x, y, z is determined by t. So based on this, we can get partial f partial x I plus partial f partial y j plus partial f partial k z k inner products dg over dt I plus df dh over dtj plus dk over dtk is 0. So again, you can see here is gradient vector. Here is the velocity. The velocity here is just for a 3D path, not just for 2D path. So you can, if we just try to visualize it, that it's just like that. If this is a P0, this is a 3D S, Y, and Z. Then if this is P0, then following all different paths, maybe follow this path, maybe follow this path. So I just use yellow is because G, H, K may be varied, because maybe they just follow this path, maybe follow this path, and maybe also follow different paths. No matter which path, one thing is common. What is that? If you just give me the P and then I give you the F function, right? I gave you the F. So when I give you the F function, when I give you f of x, y, z is equal to c, then we can define the service, right? Because f of x, y, z is equal to c, that means we just define the curve, right? So P is on this service. P is on this service. Then we can know there are many paths passing through P0, through this point P0. Then one thing one common thing just happened that we always can get the same gradient, right? Because did you remember how can we calculate gradient? Gradient vector we must know is f function. It's f function, and also the P0 point, right? So no matter the curve is this one or this one or this one, they passing the same point to P0. Then follow this function, we can know its gradient vector is the same. So based on this, we can know if passing P0, then its tangent, its velocity should be, for example, follow this one, its tangent, its velocity is this direction. If follow this solid line, its direction would be, its velocity is this one. Then if follow this one, its will be follow this one. Maybe the color is not so obvious. Okay, this is a blue one. So all this one just construct the tangent plane. Passing then they all orthogonal to the velocity, the gradient vector. So through this velocity vector can construct the tangent plane, so that we can know that all gradient vector is orthogonal to the curve velocity vector, or we can say velocity vector, or we can say velocity vector. So why I just repeated 3 times? Because you can see this velocity vector is for the orange one. This velocity is for the red one. This is for the blue one. But they can, because they all orthogonal to gradient vector, so they can form the tangent plane. That means these 3 vectors just lie in the tangent plane. So please be careful. I just try to use different color. All these 3 vectors, the curve may be different, the velocity may be different according to the path, but these velocity vectors will just lie in the tangent plane. That means the green one. Okay. So based on this idea, we can easily to get the tangent plane. Then I give you an example. Then after the example, then we can go back to take a look at this concept. Okay. 我们先一个例子给大家看，然后我们再回过头来看这个想法。哦 Okay. So find the tangent plane and normal line of f of xy z is equal to s squared plus y squared plus z minus 1 is equal to 0 at p0, 1, 2, 4. Okay, so the question just described that I give you a service. So here, you can regard it as, z is equal to 9 minus s squared plus y squared, right? So you can see it is just z is equal to f of s1, right? It's just trying to describe a service, right? I give you this function, I give you this equation. This equation is just talking about a service, right? So if you just rephrase it, you can see actually it is just with the form z is equal to f plus 1. So it's just talking about the service. So I can just also draw the service for you, that S, Y, Z. Then the shape is something like that. Something like that. So this is Z is equal to 9 minus S squared plus Y squared. Okay, and right now, let's just point out the point we are interested in is P0, 1, 2, 4. 1, 2, 4 is on the surface. 1, 2 unit, 1, 2, 3, 4, right? So this is a space point. This is space point. 1, 2, 4. Okay, so the question is just ask you to get the tangent plane. So if this is surface, this is surface, right? And I give you the point here, can you just get a tangent plane? Tangent plane. Okay, so just like when we just talk about two dimension. For 2 dimension, this is curve, this is tangent line. 二维的时候呢，这是个曲线，这是一个切线。到了3维的时候呢，它是一个曲面，问的是切平面 tangent plane. Tangent plane is trying to get tangent plane is something like that, passing through 1, 2, 4. Okay, and its normal line. Its normal line is just this vector just perpendicular to the plane. Normal line is just if this is a tangent plane. Okay, this is a tangent plane. The normal line is this one. Okay, so this is the question. This is the description about for this question. Okay, so based on the fact we learned here, the tangent plane is orthogonal to the gradient vector. So for S, we need to get the gradient vector first. So gradient F at P0 is equal to partial F partial X over partial Y partial F partial Y, then partial F partial Z at P0. So we can get the gradient vector will be 2x, 2y, 1, then 1, 2, 4. Right? For you, get the gradient vector is not that hard because you just get partial F, partial X, partial F, partial Y, partial F, partial Z. Then we can get the gradient vector. So the gradient vector here is 2, 4, 1. 2, 4, 1. So that means this vector is 2, 4, 1. So when we want to construct the tangent plane, so just think about it. Any point on this plane, S, Y, Z. If we just any point here, S, Y, Z, any point here, S, Y, Z, this point is in the plane, then we just make a vector. Make a vector with this one, make a vector with this one. So we can just make a vector for xyz to 1, 2, 4 to xyz. So minus 1, 2, 4. So any point xyz is varied, but xyz is in the tangent plane. So we try to get the formula for xyz. So when we just make a vector from 1, 2, 4 to xyz, so we can get the vector, right? All of these vectors is orthogonal to 2, 4, 1. 2, 4, 1 is gradient vector, right? Is gradient vector, right? Should be 0. Should be 0. This is gradient vector. This is the vector from any point xyz to from any point from 1 to 4 to any point xyz. Then when we just make its inner product, then we can get 2 times s minus 1 plus 4 times y minus 4, 2, then plus 1 times z minus 4. Then finally, we can get the tangent plane. Will be 2x plus 4y plus z is equal to 14. So this one, okay, and then you can get this one. This is the first, the answer for the first subtraction. The second subtraction is this is tangent line, and we want to know what's the normal line. As for the normal line, it will just follow the gradient vector. So the normal line can be described as a parametric equations. Then it will be x, y, z is equal to 1. The start point is 1, 2, 4 plus 4, 2, 1, then t. Now, you can see the tangent, the normal line is this way, right? So the start point is 1, 2, 4, but follow 2, 4, 1 directly. So you can use the start point and its normal vector to construct a normal line, just like this one. Okay, so this is a simple question. So let's just also go back to the original idea. If I give you f of x, y, z is equal to c, that means you can just rephrase it. You can know this is a service, the y service. And if just along a smooth curve, if there are same, in this case, I just depict 3 smooth curves here. One is the solid line, one is the dotted line, then the one is the dashed line. Of course, many curves passing through P0. But through this discussion, then we can know, no matter your curve, what the curve is, then the common thing is, once you get the gradient vector, their tangent line, their velocity vector could be orthogonal to the gradient vector, so that you can just construct the tangent plane. You can construct the tangent plane because all velocity vector are lying on in the tangent plane. This is tangent plane. Green one is the tangent plane. So let's also go back to the physical example, just like this one. I give you a plane, just a surface that's like this one, passing this point P0. So you can just rephrase it as this one, then you can just know actually it's just a surface, right? It's a surface. Why surface? Then the first thing for us is try to get its gradient vector. So the gradient vector will be follow this one because we already know all velocity vectors will just are orthogonal to the gradient vector, right? So using this one as its normal vector, then if we want to construct the tangent plane in red, all point x, y, z, when we just form a vector from the origin point 1, 2, 4 to x, y, z, we can form a vector. Maybe this one, or maybe this one, or maybe this one. But no matter this one, or this one thing is in common. These three vectors will be orthogonal to the gradient vector. So we just use this vector, typical vector, to be inner producted with the normal vector. So through this we can get its tangent plane. Then if we want to describe the normal line, we also can use the parametric equations to describe this one. So any point in the normal line x, y, z is one of its passing point is 1, 2, 4. By following 2, 4, 1 this direction, then we can construct the normal line as a parametric equation. 这个题目的意思就是要大家去算这个切平面那切平面当然是在曲面上面才会有的事情，对不对？那如果大家觉得这样有点复杂呢，不妨回去前面这边有看过，就是说这是曲线，曲线的话我们就会考虑取的是它的切线，因为它是2个纬度而已，对不对？曲线的话就搭配的是切线。曲面呢是有3个变数，对不对？3个变数的，那它搭配的就是切平面。所以呢，那根据这个推导知道，就是事实上你的 gradient vector 就是你的法线向量，就是这个切面的法线向量。透过这个法线向量呢，如果你要建构这个切平面的话呢，任何一个点 XYZ 跟这个通过了1、2、4这个点建构的向量呢，它们都会正交。正交这应该画这样子。我们知道这个是正交符号，对不对？垂直。所以我们利用这个性质呢，把它做出 XYZ 跟1、2、4的向量。那它一定会跟这个法线向量2、4、1呢做正交，所以2个向量做内积以后呢，会得到0，那就建构出它的切平面。然后，如果你要建构这个法线向量的这条线法线的话呢，你可以用我们所学到参数式来做。那参数式怎么做呢？参数式因为这条线上面也有3个元素嘛，有 x、y、z， 它们呢会经过了1、2、4这个点，那 follow 什么方向呢？2、4、1，然后把 t 的参数带进去，不同的 t 就代表这条线上的不同的点，对不对？特别的情况是什么 ？t 等于0的时候呢 ？t 等于0的时候就是原点，对不对？ t 等于1的时候呢，就往正的方向去走一个单位啊，所以负的话就往另外一个方向，所以整个条线呢，我们可以用这个参数式来描述它。好，那这件事情可以告诉我们呢什么呢？我们在平面上面的时候，是不是讲过一件事情，就是如果平面上经过某一个点的直线有非常多，对不对？非常多。但是呢，我一旦告诉你斜率之后呢，再回到这观念很重要，所以要重复的讲哈。再回到这里，如果我告诉你通过的点，经过这个点的向量，的切线的直线呢，事实上非常多。但一旦我给你斜率之后呢，我们知道点斜式就可以唯一决定出那个切线的那条直线了，对不对？所以同样的概念，大家如果回到三维的，就3D 的切平面也是这样的。大家想一想，这个空间上的某一个点，通过这个点的平面有多少个平面？无穷多个，对不对？但是，一旦我给你的法向量固定了，点搭配法向量呢，你的切面呢，你的那个平面就固定了。就是经过这个点有很多面对，经过这个点有很多面，但是一旦我告诉你法向量确定了，你就只有一个平面。所以为什么2维、3维要大家这样互相配合看？其实它观念是一样的，它只是把2个维度变成到3个维度这样。好，我们先休息一下哈，等一下回来继续看下去哈。I just want to summarize the process that. Okay, so if I ask you to calculate the tangent plane to f of x, y, z is equal to c at the spatial point p0, s0, y0, z0, then the result is gradient vector f at p0 inner product with s, y, z minus s0, y0, z0 should be 0. So here is partial f partial x at p0, partial f partial y at p0, partial f partial z p0. Okay, so actually we just calculate by following this idea for the previous example. So I also can draw the series for you that once I give you this f of s, y, z is equal to c, so we can get this one, right? Then I also give you the p0, the passing point, s0, y0, then z0. We just want to get the tangent plane. So the tangent plane is here. Tangent plane is here. So any point s, y, z, you can just make the vector, right? So this is the any s, y, z to make a vector with s0, y0. So this is this one. And gradient vector is here. This is gradient vector at p0. Then they must orthogonal. So finally, we can get this one plus partial f partial y p0 times y minus y0 plus partial f partial z p0 z minus z0 is equal to 0. So this is the final result, and also describe this tangent plane. This tangent will be described like this one. Okay, so you can just make a simple comparison with, I just made a 2D condition to you that if this is 2D, right, this may be f of s, y, z is equal to c. Then this is a point p0, s0, y0. Then you can get its gradient vector. Yeah, gradient vector may be this direction or this direction. Possibly this direction or this direction. Depends on the curve. Okay? And this is the tangent. So for this is tangent plane. For curve, this is tangent line. Okay, so versus, please just make a comparison. This is for surface. This is for curve. Different, right? This is for 2D curve. This is for 3D surface. But the idea almost the same, because it's just describe tangent plane will be orthogonal to the gradient vector. Tangent line will also be orthogonal to the gradient vector. This is a gradient f at p0. But of course, this gradient vector just have two elements, s and y. But this gradient will have three elements. Okay? This is another possibility is I just try to make it in the same slide so you can just make a comparison. Plane tangent to a surface. When I give you z is equal to f of s1. So something different, right? Here I just give you f of sy, z is equal to c. But in this case, it's also possible, right? I also can give you a surface by giving z is equal to f of sy. So in this case, it's s0, y0, then f of s0, y0. So you can also make a comparison here and here. So here I just directly give you z0, but here this is s0, y0, but here is z0. Z0 comes from when I use s0, y0 as an input for f of xy. So you can get 0 here. So based on the idea is we can regard it as partial g, partial x, partial g, partial y, partial g, partial z, where we just define new function g of x, y, z is equal to f of x, y, z minus z is equal to 0. So actually, after we just converted from z is equal to f of sy to f of sy minus z is equal to 0. So you can just, I just make it smaller. Please just look at here, and also here. F of syz is equal to c. So even though I give you z is equal to f of sy, so we still can make a new function g of xyz is equal to f of sy minus z. So you can see the position f here is same as the position for g. But the difference is I just move. Originally I give you z is equal to f of sy. I just put them together, put them in at the same side, so we can get this one. So that here, if our new g is here, then inner product with s0 minus s minus s0, comma y minus y0, then z minus f of s0 y0 should be equal to 0. So we can get f partial x at s0 y0 times s minus s0 plus partial f partial y when the point is s0 y0 times y minus y0, then minus 1 times z minus 0 should be 0. So finally, in this case, we will follow this formula. But actually, they are almost the same. For this case, for this case, I give you, I make it smaller so you can have a whole picture to make a comparison. Please just pay attention to the upper part. For the upper part, I give you f of yz is equal to c. For the lower part, I give you z is equal to f of y. Actually, they can convert into the same one because you can see if I just treat it as a new g of x1, z is equal to f of x1 plus z is equal to 0. So if you just notice that this one is same as this one. So here, g is same as this one. So if we can just same as this one, have the same situation, we just follow this one, we can get, when we just get the partial g, partial x, partial g, partial y, partial g, partial z. So that will equivalent to partial f. I use my mouse. You can see partial x. So that means we will just partial differentiate for this one. So we can get partial f, partial x, s0, y0. For z, since for a 3-variable function, when we partial differentiate with respect to x, y and z are constant. So of course we just have partial f, partial x at s0, y0, right? For the second part, same as this one, right? When we just differentiate, partial differentiate g with respect to y, then we will treat x and z are constant, y is a variable. So we can get partial f, partial y when sy is equal to s0, y0. Then here is still y minus y0. For the third part, because we need to calculate partial g, partial z, so this part f of xy it is not related to z, so it is a constant. So partial g partial z, this part will be 0. But for this part negative z, when we calculate its partial derivative with respect to z, that will be negative 1. Will be negative 1. So finally we can get this one. So this depends on the conditions that the question just give you. If give you like this one, you can just follow this one. If give you f of x y z is equal to c at t0 x0 y0 0，you can just follow the output。这两个呢，我可以把它写在一起，就是你可以做一个对照比较。它只是形式上给你的题目的形式上不太一样而已，了解吗？上面它是一个 f of x y z 等于 c 的形态，那要经过 p0，这个刚刚已经解释过了，举过例子了，很容易清楚，对不对？但是也有这种可能是它给你什么 z 等于 f of x y， 要经过这个 s0 y0跟 f of s0 y0， 其实是同一件事情，对不对？那这时候呢，如果你怕这个公式不好背，你不可以去背它。你要做的事情是什么？你就把这件事情，你就创了一个新的叫 g of x y z 的 f of x y 减 z 乘 z。你注意看一下那个绿色是 match 的，它的形态刚好 match 了 g of x y z 等于0，跟你的 f of x y z 等于 c 一样。其实等于0跟等于 c 事实上一样，你可以把那个 c 搬到左边去，是一样的事情哦。好，那这时候我们如果 follow 前面的规则来看的话，这个就是要算 g 的规点，对不对？对 x 偏微，对 y 偏微，对 z 偏微，然后去乘这个后面这个实际上几乎是一模一样。那这边看起来好像为什么会觉得有点奇怪是为什么呢？因为你的 f of x 本身给你的是只有2个变数 x y， 可是你要把它创成这样子，就是变成3个变数。对 g 而言，它是3个变数，所以我们要算 g 对 x 偏微的时候。没有问题，你就对 g 对 x 偏微的时候等同于右边这个是 f 对 x 偏微，所以你是 partial f partial x，y 也是如此的。z 会有点不一样 ，z 为什么不一样呢？当你去 partial x partial g partial z 的时候呢 ，f of x 是常数，但是 z 呢它只有一个负1的系数，所以它一微分出来是负1，乘这后面这个。z 减这个 z， 所以这两件事情取决于，如果它给你的那个函数曲面的函数是不一样的形态的时候，你可以采用不同的方式，但是原理是一样的。原理你只要记得，哪怕你公式忘了，你到时候稍微自己稍微推一下，就想到这结果了这边都是比较困难的部分所以我们讲的速度都稍微缓一点点那这些都是应该都会有必考的题目出现在这几个问题上面好，那这是另外一个 gradient vector 可以用来做算法向量来算那个切平面或是切线斜率、切线等等的Okay, then we just move to next topic. The next topic I'm going to introduce to you is estimating change in a specific direction. The change, we use df, that is equal to gradient f at p0 inner product u times ds. Don't worry, I will tell you why. This can be for 2 or 3 variables or even more. Okay? So before that, I just want to remind you about that for single variable. This is for 2, 3, or more variables. We will define it as this one. But don't forget, we also learn the same concept for the function with a single variable. So at that time, last semester, we know that if I give you y is equal to fi, so this is a single variable function, right? This is a single variable function. So if I give you around a, we can just make a tangent. If it is differentiable, the slope is f prime a, right? It's slope. So if y is equal to fs, and fs is differentiable at s is equal to a, so of course we can get its slope, n is equal to f prime a. So at that time, if we want to estimate its change, it will be around f prime a times dx. This is for single variable. So you can just make a comparison. They are almost the same, right? This is the estimated change, df, is equal to, for single variable, is the derivative of a times a small change dx. So for 2 or more variables, we also can get this part is did you notice this is the rational derivatives times a small change in s ds. So we can also make a figure for this case that, okay, this is a 2 variable case, s, y, and z. This is 2 variable. Z is equal to f of y. So of course you can make the series. Then I give you P0, then also one direction U. So of course you can follow this and make a plan to cut the surface. Then you can get, that will be just like this. This is the 3D point. Then this is the curve. Maybe I can use red one. Then this is a tangent. Then this is the slope here is the rational derivative when sy is equal to s0 y0. So if you want to estimate in some specific direction, the specific direction is just follow u. So you can see if we can have a small change here. If we follow this direction, if we have a small change here, then how much change will be made by this case, right? If we have a small change here, this is ds. So how much will be changed? How much change will be made for this case? So of course it will be like the rational derivative times a small change ds. Because in this case we have several directions. So if the direction is far away, that will be totally different, right? 所以在两个变数的时候，就比单变数稍微复杂一点点，其实原理也是一样。单变数的时候，它只有一个方向，是 S 上面的 小小的改变去乘以这个它的斜率，对不对？可是，在多变数或者我们先拿两个变数来看的时候，其实我们都知道，已经到现在大家都知道，方向导数事实上它是取决于除了哪一点之外，对这个两个变数来讲呢 ，P0 就相当于单变数的 A， 大家同意吧 ？P0， 对不对？但是呢，单变数的时候不好意思，它只有一个方向的，它就只有在 x 轴上面的变化。可是如果是在两个变数的时候呢，它可能是这个方向、这个方向、这个方向、这个方向。虽然 P0 是一样的，但是配合这个曲面，你的方向一改变，你的瞬间的变化性是不一样的。这个跟之前观念又呼应到了，对不对？爬山的时候，朝着某一个面向走，它可能是下山的；朝着某个方向来讲，它往上爬的；朝着某个方向来讲，它可能是不增不减的。当然中间还有 in between 的 case， 对不对？所以它就有不同的变化的，它就有不同的陡度了，瞬间变化的陡度。所以呢，你把它的方向导出去乘以它在这个方向上面的一点点的改变量叫 dx 的话，那不就是它的这个在某个特殊方向上面的改变量吗？估计的改变量。但变数是我们是这样估计的，但多变数的时候，我们是用 gradient vector 搭配出的 directional derivative 来计算。哦，好。Let's just go over the concept by using one example that please just estimate how much the value f of x, y, z is equal to y times sine x plus 2yz will change if the point P, S, Y, Z move 0.1 units. Okay, so please just notice that in this case, I'm just talking about a two variable function, z is equal to x. But in this case, this is a three variable function. But it doesn't matter. It doesn't matter. You still can follow the rational derivative to get by using its gradient vector and the direction. You can get the rational derivative times a small change. Okay, so here you can map to this service. Of course, this is not a service, but the role is the same. 它虽然这不是一个曲面哦，这不是一个曲面，因为它有三个变数，但是呢，它的角色是跟这个 two variable 的 z 等于 f of y 是一样的。这是已经变成 w 等于 f of y 等于 blah 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 s blah 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 y 跟 blah blah z 的关系，但它的角色是一样的，这两个角色是一样的。And move 1.1 unit from P0 010 straight toward P2 P1 to -1 2. Okay, so you can see P0 is here. I'm trying to use the same color to map the rows from the question to the abstract concept here. So you can see service is here, even though E is not service, because this is a 3-variable function. And move, how much? Small move is 0.1, so from this 0.1, and P0 is here. And you can see there is a hidden information here from P0 straight toward P1. So there is a hidden information about U. Did you remember U is also a very important, right? This part is just talking about something about U. So you can see this is service, this is start point, T0, and this is the direction, then how much we can move. So let's just go here. Based on this formula, you can see this is a surface. This is the P0 point. This is the direction. Of course, in this case, we also need to have small change in S, which can cause some change for F. So we have the force. We have the force parameters. I can see here 1, 2, 3, 4. The 3 ones are original, but ds is a new one. Okay. Then how can we do that? We can start to calculate it. The first one is, let me just note it down as the formula here. P0 inner product U, then times ds. So 1, 2, 3, 4. So first we need to calculate the direction. So we can get P0 to P1 vector is 2 minus 0 I plus 2 minus 1 j, then negative 2 minus 0 k. So we can get 2i plus 1j negative 2k, right? But the vector P0 to P1 is still not a univector. So if you want to get the U, it should be P1 P0 to P10 a vector over its length, right? When we just, this is the vector, this is the vector length. When the vector is divided by its length, we can get a univector. So the answer will be 1 over square root of 2 square plus 1 square plus negative 2 square times 2i plus 1j minus 2k. So the answer is 2 over 3i plus 1 over 3j minus 2 over 3k. So this is our univector. Then the second step we need to calculate is gradient vector at P0. So in this case, we need to calculate partial f partial x I plus partial f partial y j plus partial f partial z k at zero, 1, 0. Right? We need to take a gradient vector f at p 0. So we need to take the this is 3-dimensional gradient vector so that we can get y cosine x I. Why y cosine x y? Because when we differentiate f of x y with respect to x, then y here will be treated as a constant, z will also be a constant. So only y times sine x will be affected, but for y2, yz, since they are constant, so when we differentiate with respect to x, that will be constant. So we can get y times cosine x times y, y times cosine x I. Then we also have sine x plus 2z. Follow the same rule, plus 2y k. When syz is 0, 1, 0. So the answer is 1i plus 0j plus 2k. So right now we already have this one, gradient vector. We also have the unit vector here, so that we can just continue to get df is equal to the gradient vector 1i plus 0j plus 2k inner product, this unit product, then times a small change is here, ds 0.1, so that the answer is negative 0.07 units. So that means based on the estimation, the value will decay 0.067 units. Following this situation, following this service, following this small movement, following this direction. OK， 好，所以这个题目呢，虽然看起来跟刚刚我介绍给大家看的时候是2个变数的函数哦，这个是2个变数函数，可是它等同适用于3个变数的哈，所以我们直接举的例子里面是课本里面的例子是一个3个变数的哈，是个3个变数的。那它呢，这里面呢，当你要去，这个是公式哦，这是公式。那这个公式呢，我刚才跟大家解释了，它的原理也是来自于类似像单变数的时候一样，现在算出它的导数，对不对？在这里呢是方向导数，是来自于 gradient vector 去跟单位的向量去做内积而出来的。所以如果这个公式怎么来看呢？你想要知道这个方向的微小的变化呢，取决于这个方向的方向导数跟在这个方向的微小的变化 ds。所以呢，总共就会有4个重要的因子来影响这个最后的改变量。前面3个大家都很熟了，对不对？前面是 gradient vector， 这 gradient vector 再复习一下 gradient vector， 方向导数有哪3要素？第一个，曲面的方程的函数，再来在哪一个点？再来往哪个方向？ 所以这个大家是熟悉的，对不对？你们讲了很多次。唯一不一样是我们多增了一个在那个方向的微小变化。那微小变化呢，刚刚也解释过了，在单变数的时候，其实我们做过了，斜率去乘以它的 S 方向的些微变化，所以在多变数的时候去乘以一个这个方向上面的些小小变化。所以当这个公式列出来之后呢，我们就去抓出这4个重要的参数。第一个 F 有没有？有，就是白色那个，对不对 ？P0 有没有？它是说从 P0 往 P1 走，所以这个交代2个讯息，一个是在哪一个点的gradient vector P0，它是往哪向走，告诉你的方向了，但是这还不够，我们必须要是单位向量，所以呢，我们等一下要把单位向量化，那最后一点点的移动量是0.1，所以看起来每个元素我们都具备了。所以一开始要算的时候，先把 U 给算出来，因为这里 U 不是直接把 P0 到 P1 的向算出来，它算出来之后呢，还要做单位向量化，就把自己的向量去除以它自己的长度。那这个部分是把 U 算出来，那这个部分呢是要把 gradient vector 算出来。那 gradient vector 我们算了很多次了，这边是3个变数的 gradient vector。好，所以在 P0 的这个点的条件下，是它得到是这个，所以我们就把这2个内积完之后呢，再去乘以这个 0.1 的变化量呢，我们就可以得到负的 0.067 单位，代表什么？沿着那个方向呢，它的曲面啊，往着那个方向走的时候，它的微小变化走了 0.1 的时候，它是往下降的。好，那接下来我们要讲到2个变数的线性化，这我们礼拜4在讲，因为这里面每个观念都很重要，但是请大家在复习这一块的时候，就记得回去看一下单变数的时候，其实我们讲过是什么概念，很多观念事实上都是相同的，只是它变成2个变数或者3个变数。那有关于这个线性化还有全微分的部分，我们就礼拜4再讲好了。因为剩下4分钟，这个可能讲不完。好，那我们今天就先上到这里哈。今天没有上很多哈，总共只有5页而已哈，所以好，我会把它消化一下。